So in this chapter, chapter number 5, we're going to look at some of the performance parameters of feedback control systems. How do you measure the performance of feedback control systems? Some of the stuff we are going to look at in this chapter. We're going to look at different input signals as how they affect the output and the error of the control system. Again, as we've been discussing over and over again, what is the main advantage of closed loop control system is over the open loop system, we can adjust the steady state response, we can adjust the transient response, both of them, by adjusting the parameters of the system of the controller. And we can bring the output to be as close to the actual response that we want the output to be, which is the input. You as a control engineer, design engineer, you need this, you're writing the specifications of the system, design the system, test the system, revise the system, troubleshoot it, and all those things basically. An electrical engineer or control system engineer, that's what he or she has to do. Every system has some operating conditions, and those operating conditions need to be met in order for the system to have optimal performance. Specifications are stated in terms of performance, indicate quality of the system to the designer. In other words, performance measure help to answer the question, how well does the system perform the task for which it was designed? That's the basic goal. You're measuring the performance of the system, that it is doing what it is supposed to do. So what we're going to do in this chapter, time domain transient and steady state performance of different systems will be analyzed. For some commonly used input test signal, response of a system based on the location of its poles will be discussed. We're going to discuss what do you mean by poles. Many of you are familiar with the term poles if you took DSP with me. It's the same thing again. DSP is what we are doing here. DSP is pretty much the digital counterpart of what we are doing here in the analog domain. And we are also going to go over some of the important performance parameter in which the system response, the system is measured. The performance of the system is measured. So first, what type of test input signals do we use? So far, we've been using mostly unit step function. We're gonna kind of broaden our range of signals, and many control system experience actual input signals that are very similar to the standard test signals. Furthermore, using a standard input signal allows the designer to compare several competing designs. The common test input signals we are using, again, the first one, unit step. We have not used unit impulse so far. Ramp input we have not used, and parabolic signal we have not used. Now, once again, ramp signal and parabolic signals, you cannot let them go forever. Otherwise, they are going to become unstable, right? They're going to keep on increasing with respect to time. Unit impulse, again, impulse means that its height is infinite and it occurs for only a very small period of time, infinitely small period of time. That's the unit impulse signal in analog domain. Unit step is the only one in this case that can go on forever and it is stable. Ramp and parabolic are not stable as t tends to infinity, so you have to use it within the time constraint. So unit impulse, as I said, exists at only one instant of time, and its area is supposed to be 1, not 0. It's supposed to be 1. I don't know why did I write down 0, which means that its height tends towards infinity. Laplace transform of unit impulse is simply 1. So what is unit impulse signal? Unit impulse basically is that if you have, and I can do it on the board, in analog domain, unit impulse is basically a pulse, and the pulse has some height. Let's say the height is h, and the width of the pulse is 1 over h, such that the area of this pulse is 1. Height times width, the area is 1. If you keep squeezing the width and you want the area to be still 1, then you have to keep increasing the height, right? If you want to keep the area 1. To the point that you want the signal to occur only at one instant of time, and that's it. And if you still want to keep the area to be 1, then the height of this impulse is going to be infinite. So that's what impulse signal is. Impulse signal is a mathematical signal. It does not exist because, again, magnitude of a signal to be infinite, it does not exist in the real world. But the approximations approximations to the impulse signal are generally when lightning strikes, basically, and a large amount of current flows in a very short amount of time. That's closer to what an impulse is basically in reality. That some large signal is taking place in a very short amount of time. That's basically the physical explanation of an impulse signal, as simple as that. Because mathematically it exists, physically no signal can have the infinite height or infinite magnitude. But any signal that is happening for a very short amount of time and the value of that signal is very large, that's assumed to be an impulse signal. Laplace transform of impulse signal is simply 1. Since it is not easy to produce an impulse signal practically, the other 3 signals are more commonly used to analyze the performance of control systems. That is, a step signal, ramp signal, and parabolic signals. Figure 5.1 shows the common signals right here. So standard test signals have the form input is equal to t to the power n. N can be 0, 1, 2, 3, 4. When n is equal to 0, it becomes an impulse signal, a step signal. And n is equal to 1, it becomes a ramp signal. N is equal to 2, it becomes a parabolic signal, and so on and so forth. And the Laplace transform is simply given by n factorial over s to the power n plus 1. So the step signal, which is right here, n is equal to 1. So RT is equal to A. You can multiply this by A times Tn. RT is equal to A. RS is equal to A over S. And ramp signal A times T. And RS is equal to A over S square. Parabolic signal A times T square. RS is equal to 2A over S cube. So these are the Laplace transform of the parabolic step, ramp, and parabolic signal, and these are the signals that we are going to use as our test input signals. Determine the unit step response of the following closed loop control system. Also determine the steady state error. Again, this is just a practice because you have done it quite a few times. All right, step response, that is the output when input is a unit step signal. So first, let's write down the output. The transfer function is simply gs over 1 plus gs, which is equal to 2 over s square plus s plus 2. That's your transfer function. And your output y of s, which is in this case c of s. Let me change this c to y because I'm so used to writing y of s, is ts times rs, 2 over s square plus s plus 2 times 1 over s. All right, partial fraction decomposition and inverse Laplace transform can give us, open the MATLAB, it's right here, Let's apply partial fraction decomposition on this. And we get 1 over s 1 over s plus negative 0.5 plus j 0.189. So I can write down 0.19 divided by s plus 0.5 minus j 1.3229. So 1.23. 1.3233. Yes. This is your A, and negative 0.5 minus j 0.19 over s plus 0.5 plus j 1.32, and this is your A conjugate. Okay. See if you're getting the same result first of all before we move on. Apply the residue function, see if you're getting the same result. Good. All right. When we take inverse Laplace transform, Anybody remember? Well, the first one is easy. Anybody remember for the complex part? What do we do with the complex conjugate fractions? What is the inverse Laplace of those? First, we convert the numerator into polar form, which is 0.53 angle 159.29. You can look at the table, of course. Anybody remember what was inverse Laplace? 2 times the magnitude of the numerator e to the power alpha t cosine omega nt, omega n is 1.32, plus base of the numerator. This we did in chapter number, I believe, 2, one of the Laplace transform pair that we discussed. I did the whole derivation, and then we concluded, or we deduced this result. Let me open that real quick for you. Slide 11. This right here. 2 times the magnitude of the numerator, e to the power negative alpha t, where a is equal to alpha plus j omega n, cosine omega nt plus angle of so that is the closed loop response, unit step response. And steady state error, we can just do it here. What do you think the steady state error is? Error, we're talking about error. No, steady state error we are talking about, remember. Steady state error. Not the you're telling me output, a steady state output. So what will be the error steady state? 0, exactly. Because remember, input is what? Unit step. And the output steady state value is also 1. So when you take the difference between the input and output steady state values, that's 0. So you don't have to, I mean, you can of course do the derivation and everything, but you don't have to do that. You know that the output steady state is 1, input is also 1 steady state value. So the error between the two is going to be 0. Since RT is equal to UT, which is 1, and Y steady state is equal to 1, which implies E steady state, which is R steady state minus Y steady state equals 0. Before that, you will have some error between the output and input because the output has a transient response. But once the transient response is gone because of this exponential decaying function, this is going to make the transient response to go down to 0. Steady state output will be 1, and the input, which is equal to the desired input, which is 1. Therefore, the error is going to be 0. All right, let me show you now. I think it's coming up somewhere, but it's a good time to show you because the time is a little short. So let me show you. If you, of course, if you want to plot the step response, then you can always plot this function versus time, and you can have a plot of the output for your unit step input. Before I do that, let me ask you a question. If you are plotting this, how long you are going to plot the response against time, and let's say what step size you think you will be taking, and that will be not 0.5 over 1 over 0.5, but that's the time constant. So how many time constant? You said 5 approximately. Okay, 4 to 5 time constant. And what should be your step size for a good clean graph? Yeah, usually that's what I take, about 1/100th of the time constant. That's what I take, 100 points per time constant. So 500 points total. You can take 50 points, and I think the response may still be very good. But you don't want to take very small step size. Like you don't want to plot 2 points per time constant. Otherwise, your response is going to be like all straight lines and sharp edges. So yes, 1 over 0.5 is basically the time constant of this part. So it's going to increase, of course, it's going to increase towards 1, it's going to have a dip, and then it's going to become constant. And you want to plot it for approximately 5 time constant. So the time constant is, this is 2 seconds, 1 over 0.5. So you want to plot at least for 10 seconds, let's say, and 8 to 10 seconds with a step size of 1/100th of the time constant. So that will be a good time vector to plot this. Now in MATLAB, if you do not have this, but if you want to plot directly from the transfer function, then you have to do, let me show you, you have to do 2 things. CLC. So first you are going to define the transfer function. So let's say my transfer function is TF is the MATLAB built-in function to create the transfer function. TF, I believe we have to do system. Let me see if it works or if it is system. And my transfer function is 2 over, so 2, and the denominator is 1, 1, 2. So the coefficient of your polynomial. All right, function belong to control package. Okay, package load control, PKG load control. All right, let's go back. So it created a transfer function, 2 over s square plus s plus 2. That's our transfer function. And then we have a command, step, to plot the step response. So step transfer function, and if you just do a step transfer function, it's going to plot the step, or you can also give a time vector after that, so it's going to plot for that time vector. And if you don't give time vector, it's just going to plot for default time vector. I don't know what is a default time vector, but let's see. If you do the step df, come on, then it's going to plot the step response. It is going up to 10 seconds, so about 5 time constants. So if your goal is only from the transfer function to plot the step response and then observe the characteristics of the system from that step response, then you don't really have to go through inverse Laplace transform and all those to write down the time expression. You can just use in MATLAB, first define the transfer function, and then use the step to plot the step response for that transfer function that you're defining. Now from this response, of course, we can see the peak overshoot, all these things we're going to discuss, peak overshoot and the steady state value and all those things. So MATLAB control system toolbox has many control system built-in functions that we can use. Some of these functions, of course, we are using residue. Of course, that's not for control system, but residue is just for the partial fraction decomposition. These are specifically for the analog control systems, step response and the transfer function. And I believe I do have somewhere over here. Let me delete this slide real quick. Oh, right here. It's right after this slide. Transfer function and then step. So it is given over there. And oh, same thing, basically plotted the transfer function. Okay, guys. So I believe we should stop here. And then we will continue from this point on next week. Let's save this thing.